Hello. In this lecture, I will introduce you to a number of ways to organize and record ideas in solving problems. In this part, we will have a look at flowcharts and pseudocode. In the second part, we take a look at mathematical models. Do not hesitate to pause the video to have a think or investigate what you see, even if I do not explicitly suggest you do so in the text. When we deal with complex problems, we need to have a way to organize and record our ideas. In addition, we may need to communicate our ideas to others. But what kind of ideas are we talking about here? When we solve problems, we try to identify or develop methods for it. A method is a list of clear steps to reach a goal. In mathematics and computer science, we call a method that always requires a limited number of operations an algorithm. There are many ways to record ideas. For the specific type of ideas we call algorithms, we can use flowcharts and pseudocode. Let's have a look at flowcharts first. A flowchart is a diagram describing an algorithm, workflow or process. Programmers often use flowcharts to describe their ideas. Let's have a look at one. This flowchart describes an algorithm for returning the smallest of three numbers, a, b, and c. So how do we read a flowchart? Well, we start at the element that is marked with start and follow the arrows wherever they go. So first we encounter a rectangular element that has an instruction step. It says input a, b, and c. Input is just a hypothetical imaginary command which gives us values of a, b, and c. Then there is a diamond there that indicates a decision. And you will remember that the bracket, the angular bracket in that direction means less than. So a less than b question mark is basically a test. It tests if a is less than b. We then follow the yes or the no based on the value of a and b, the result of the expression. Then there are other rectangular sections where it says return. Return again is a command that is imaginary in this case and just says we return the value of c or a or b depending on how we followed the flowchart. Finally, all the arrows will end up at the last element, which is the end of the algorithm. Pause the video and take some time to follow the arrows and the decisions from start to end, so that you actually understand what is happening. You have total freedom in making flowcharts. You can write natural language in the elements or some code like pseudocode. But if you want that others can understand your flowcharts, it is a good practice to follow a few simple rules. Use rectangles for describing a status or instruction step. Use diamonds for decisions. Never mix decisions with instructions. And connect all the steps with arrows. Also mark the start and the end of the process or algorithm. Flowcharts are particularly effective when drawn on a whiteboard while presenting or discussing ideas with nontechies. They can be part of a formal design or just simply part of your own notes. For larger, more complex ideas, they can become a bit of a nuisance to create though. Luckily, there are many tools available for creating flowcharts. For this course I am using draw.io, which is a free online tool for creating many types of charts. Making flowcharts is nice for quick visualizations and presentations and all, but for anything more involved I rather juggle chainsaws. So luckily there is pseudocode. If you need to record your ideas for an algorithm or a system as part of the design phase, it can be much easier to use pseudocode instead. Especially if the target audience is you and/or other hackers. Pseudocode is a human-readable code. It is not intended to be used by a computer as a program, but only to document and communicate algorithms, processes, etc. Let's have a look at the previous algorithm, but now in pseudocode. As you can see, we ignore all syntactical rules of programming languages in pseudocode. So how do we read pseudocode? This little code here is doing exactly the same as the flowchart. The only difference being instead of start and end, I created a function. But I could just as well written start here and end there. But for now I create a function that is called smallest. And then again I use the input command to get values for A, B and C. Now this is read as if A is less than B, then if A is less than C, return A. If A was not less than C, if this is false, then we return C. Now if A wasn't less than B, we test if B is less than C. And in that case we return B. Otherwise we return C. You can even write natural language in pseudocode and then you write down what I just said. Or something like it. You can mix these two things, it doesn't really matter as long as it is really clear to you. And to the people you're making the pseudocode for, of course. Just as flowcharts, pseudocode can be seen as a recording of a mind map. I encourage you to be creative when you create pseudocode, because there are no rules. Now is a good time to pause the video to study the code and see if it makes sense to you. There are a few things that you have to know so that your flowchart of pseudocode effectively and clearly describes an algorithm, and that it can be understood by others. There are some common constructs in languages that describe algorithms. Even flowcharts can be seen as a language and you can express the same constructs in them, and quite often you will use pseudocode in the steps of a flowchart, as I did before. Algorithms are described by using variables, sequences, loops and decisions. You will use these constructs in flowcharts and pseudocode, but also in many programming languages. In programming languages, there are strict lexical and grammatical rules for applying these constructs, but in pseudocode we can ignore all that. In flowchart and pseudocode, we are only interested in communicating or documenting ideas. Let's start with variables. You will need to deal with values of various types, like numbers and text strings, but also complex types like address, date, list, set, tree, and even function. A variable is a named value. By the way, when I write something in yellow, that means that is a particularly important little piece of information, kind of a definition. If you need to set the value of a variable named counter to 10, and then assign the value of counter to another variable called start, you would do something like this. In pseudocode, you would write counter becomes 10, start becomes counter. In a flowchart, you would make two steps, and you could choose to put one of the instructions in each. So counter becomes 10 is one instruction step, and in the next one there is start becomes counter, connected with an arrow. You could of course have written this in different ways, but this is how I did it here. In this course I will use the colon equals to assign values. You should read the colon equals as becomes. It's not a rule, but simply a convention I choose in this course. You will find that it is a common choice for pseudocode. More complex types can have hypothetical functions or indices. You may have noticed that I use the double forward slash to start a line comment. Everything after the double forward slash on the same line is not part of the code, but just a description. So in this case, up here, it says set I to the 11th element in the list. And that refers back to this statement, which is I becomes the 10th element of the list. The square brackets are common notation to give an index into list, but more about that later. List is a variable containing a sequence or an array, and I chose to address the elements in the list using the square bracket notation. But you're totally free to use other ways, like using a function. You can write list.getIndex, where index is the parameter to the function get. It is the 11th element we get because I chose the first index to be 0. You have to remember that everything is hypothetical, so you can imagine all kinds of cool functions and data types. It is normal that certain elements of your pseudocode resemble how you would write it in your favorite programming language. As mentioned earlier, in pseudocode, we do not need to think about syntax or the function, or if the function day of week or the command print actually exist. Commands like print can also be written as functions. Everything is possible. Our only goal is to describe an algorithm. Most important is that you understand that every operation happens one after the other, that it is a sequence of operations. Sometimes there is a certain order in which the operations are performed if they are part of an expression. Obviously, the function day of week is called before the print command. When you use arithmetic operators like plus, minus, times and divided by, in expressions it is common to evaluate those expressions using the normal rules. A sequence is a group of one or more operations that are performed one after the other. Now 99% of all pseudocode you will see is biased towards the empirical programming paradigm. We will discuss programming paradigms later in the course. That is fine for now, and it corresponds with how processes work, but it is certainly not a rule. To illustrate that, consider the following version of our smallest of three algorithm. In this case, there are two functions. One function that takes the minimum of two parameters, x and y. If it returns x if x is less than y, otherwise y. The other function takes the minimum of the three, or the minimum of a list, and the list consists of A, B and C. In this function I call the previously defined function min. I take the minimum of A and B and C. Think about it and it makes perfect sense. That which is different in this notation here, the way I wrote the pseudocode, is that I do not use return or anything. The function simply takes the value of whatever it is that an expression evaluates to. So x, if x is less than y, otherwise y. And here I write the minimum of something. The function just returns basically the value that was the last result of an evaluation. Now, in that sense, functions here behave much more like mathematical functions, and sequences become much more governed by evaluation order. This pseudocode is more in line with the functional paradigm, but it is also quite clear in describing the algorithm. I would say even more clear. When you describe algorithms, you will often need to choose which sequence needs to be executed based on various conditions and decisions. In that way, you can control the flow of operations in an algorithm. Decisions can be coded using the if-then-else construct. In pseudocode, we already seen it, or partly, and you would write down if A is less than B, for instance, then print A. Of course, this is an example. Else, print B. In a flowchart, you would draw the same thing by using a diamond, which is the test, A less than B, and then, based on the result of that expression, follow yes or no. And that would result in the print A or print B statement, or instruction step. As I mentioned earlier, your pseudocode will often resemble programming languages you use, so I use if-else instead of if-then-else. You see, if A is less than B, print A, else, print B. Also note that the indentation is very important in pseudocode. In pseudocode, a sequence is defined by a group of one or more operations with the same indentation. So looking at this example, when no else is used, it's only the indentation that gives you information of what is meant. If A is 2 and B is 3, the output is the following. But what if A is 3 and B is 2? Well, then only the last two print commands are executed, because A is not less than B. And if A is 3 and B is also 3, same thing. The value of B is 3, because A is not less than B. Now think about how you would draw the flowchart for this algorithm. Now, it should look something like this. You choose which way yes and no go. Both diagrams have the same meaning. Sometimes you need to execute a sequence several times in succession. Maybe we changed values for certain variables for each iteration. To write down such situations easily, we use loop constructs or loops. Loops combine all the constructs we have seen so far: variables, sequences, and decisions. Here are 3 common loop constructs: the for loop, the while loop, and the do-while loop. You choose which construct best suits your case for each loop. Let's look at an example of each construct. Okay, here is an example of a for loop. I've written down in the pseudocode 2 versions of the same loop. The second version is more C, C++, Java-like, but it means exactly the same in this case. The second form allows for more complex loop control, but we get to it. First, let's have a closer look at the first form. You can read the first form as let counter take the value of each value in the series 0 to list length -1 successively, and for each value execute the sequence. The sequence that is executed in a loop is often called the loop body. In this case, the loop body is print list counter, where counter is the index in the list. In the first form, the decision is not obvious as the loop is defined by a series. Now the second form we can read as: first initialize the counter to 0, and if counter is less than the length of the list, execute the sequence. Then increment counter with 1 and test again. So first counter is initialized with 0, then counter is compared against list.length. If it is less, we execute the loop body. Once that is finished, we increment counter with 1, and I will get back to the notation of ++, and then we go back to testing counter against list length. And as long as counter is less than the list length, that will continue. Once counter equals list length, or gets bigger, we leave the construct. Counter ++ is another way to write counter becomes counter +1. The second form is more versatile, but remember that there are no rules. The thing that is at most convention here is the use of the word for. Now here is the flowchart for the same loop. Now let's write the same thing using a while loop. Read this as: while counter is less than the length of the list, execute the sequence. In this case, the code relies on the value of counter being initialized outside of the loop construct, and that it gets incremented in the loop body. And in the code here, counter is initialized to 0, but the loop construct begins with the while, and the counter is incremented as part of the loop body. Now notice that the flowchart I made for the for loop is really a while loop, because this flowchart is exactly the same. Now almost the same thing using a do while loop. Read this as: execute, or do, the sequence while counter is less than the length of the list. Why almost? What is different here? The loop body is executed at least one time. That's very important here. This is because the test, while, is done after the loop body. That is why you will only use this construct in very specific cases, while the other two are more or less interchangeable. Counter got initialized, then the loop construct starts with a do, and the loop body is executed without any tests. So it's done once. The test is done after the first time this is done. If counter is less than the list length, it will repeat the loop body. If not, it will continue. The flowchart for this looks something like this. Conclusion. These fundamental constructs make it possible to describe every algorithm that can be thought of. They have their counterparts in almost every programming language. At the same time, you should not feel in any way limited by them when writing pseudocode. Essential fact of Guerrilla programming. If you can analyze and solve problems and then describe your solutions using pseudocode, then you can program. The choice of programming language should only be a best fit for the implementation of your solution. Programming itself is independent of that choice. And this ties back into the definition of Guerrilla programming, which said that the shape of a program should only be defined by the problem it tries to solve. All you need to start solving problems is paper and a pencil, but luckily there are plenty of editors out there to help you write code, and even pseudocode, of course. To name a few, I use Emacs, Atom and Eclipse. All of those are free. This lecture would not be complete without discussing another extremely important representation of ideas, and that is abstract mathematics. But as you already have plenty of stuff to review, I will leave that for the second part of this lecture. I hope you enjoyed this one, and see you in the next one. Bye bye.